calculations with strain, I always recommend using smaller units with that. Otherwise, things can get kind of weird actually, or you lose meaning in some of the calculations due to rounding because the strain values are typically very, very small. So I always recommend when calculating strains using smaller units, and that goes for deflections and deformations as well. So just keep that in mind. And then also along those lines, because strains are typically very, very small, you can neglect any strain products that show up in calculations. So this will come up in homework 2 in one of the problems where you're asked to calculate the change in volume of a plate, I believe. So when you calculate the change in volume, you'll end up with some expressions or some terms that have, strain in X times strain in Y, for example. You can neglect those products because they won't contribute much at all to the final answer. All right. So now, moving on to orthotropic materials. We have, with an orthotropic material, all right, so a couple of things that are important to note. The principal axes of stress are not going to be the same as the principal axes for strain if the material is orthotropic. So that's a new concept for this class anyway. So instead of those principal axes tied to stress and strain, we usually use what we call the principal material axes. And so this is well explained using wood as an example, because the one material axis will be along the length of the grains of the wood, right? And another material, or another principal material axis would be perpendicular to that grain direction, right? So again, using wood to envision this, all right? Here's a wood plank with the axes oriented along the principal material directions in 3 dimensions, and then an example of plane conditions, right? Maybe a oriented strand plywood board or something like that for the plane conditions. And the reason we want to use these material principal axes is because remember that the material will have different properties in different directions. So those directions designate the material principal axes. So for example, if we align our X and Y axes along the principal material directions, then we would have a Young's modulus and a Poisson's ratio associated with the X direction, and a Young's modulus and Poisson's ratio associated with the Y direction. And these values would be determined through experimentation. So an example of the tests that would be conducted to determine those properties is outlined next. All right, so if we consider a single ply that is aligned with principal material axes, then I'll sketch it on here. So we would have like a rectangular section or a rectangular sheet of ply. We would use separate tests for these segment 1 and segment 2 tensile tests, or separate strips is what I wanted to say. So maybe we cut a strip like that for the first test, and then cut a strip in the other direction for the second test. It doesn't want to cooperate with what I want to do. There we go. All right, and then the remaining panel we would use for the shear test, which we'll look at on the next page. But first, let's consider these tensile tests. So we'd take this first strip, all right, and apply a normal stress that's oriented along that first direction. All right, so this would be the 1-2 orientation for that strip. And then we would measure the strains in both the orthogonal directions, right? So as it stretches along the 1 axis, it would shrink in the 2 axis. So we would have normal strain in the first direction is equal to sigma 1 over Young's modulus associated with that direction. And the normal strain in the 2 direction would be equal to negative Poisson ratio subscript 1-2 times sigma 1 over Young's modulus for direction 1. So then for the second test, all right, so this would be the 2 direction of the material, and then let's see, to be consistent, we'll call that the 1 direction, positive downward. So we would apply a normal stress in the 2 direction, and the strains that we measure, all right, would be, I guess I'll just write them 1, 2. So in the 1 direction, it would be negative Poisson ratio subscript 2-1 times sigma 2 over Young's modulus in the 2 direction. And then strain in the 2 direction would be just sigma 2 over capital E2. All right, so then the third test would be for shear. All right. And for that, you would apply a shear force to this rectangular panel. And measure how much the angle changes. All right, so that's your shear strain. And then you can calculate the shear modulus from that. All right, so we're going to come back to that sequence or those test results, but now I'm going to take a step back and lay out the general process for determining end results. All right, so relating, our end goal is to relate stresses and strains in the XY, right, orientation. And the XY may or may not be aligned with the principal material axes, right? So 1 and 2 are the principal material axes. X and Y are what we would use in our, analyses or whatever, depending on how strain gauges are aligned or, whatever it is that we're looking at. So, but we want to be able to relate relate them no matter what. Of course, it's most convenient and ideal if we do align the 1, 2 axes with x and y, but that's not always the case, so we need these tools. So I'm going to label these steps, and then I'll summarize them at the end so that they all kind of come together. So the first step is to transfer the coordinates, right, from whatever you have to the non-principal material axes. And remember that stress transformation is based on equilibrium. All right, you may have seen that derivation in mechanics of materials, probably in lecture, and then maybe never did it in practice, but that's where it comes from. As a reminder, it's based on equilibrium. And another note, we'll consider the angle theta to be positive counterclockwise from the x-axis to the 1 direction. So then this first matrix equation, I'm going to call 1A, all right, because it relates the stresses in the material principal axes to the stresses in the x, y directions. And then if we rearrange that equation, we have the reverse path, right? So I'm going to call that one 1B. So that relates the xy to the 1, 2. Or I guess solving for xy instead of solving for 1, 2, right? And this matrix T, right, T for transformation, is just based on geometry that comes from the equilibrium, right? So if you were to break it down, draw a free body diagram of an element, and then write out all the equilibrium equations, you would find an arrangement that's consistent with this matrix. All right, so now we're going to apply the same thing to strain. So I'm going to call this equation 1C and 1D over here. All right, so the 1 phase is just all coordinate transformation. And the transformation matrix for strain is similar to the transformation for stress, but it's not identical. All right, so you can see the difference is in the last row and the last column. They're essentially, I think, are they transposed? They're transposed and the signs are a little different, right? But other than that, process is the same. And I'll note here, all right, so unlike stress, strain depends on deformation compatibility. All right, so then on the next page, this is where those tests that we looked at earlier come into play. Now, if we superimpose the results of those tests, we get our constitutive equations, right? The relationships between stress and strain in the principal material directions. So we're going to call that phase 2, right, relating stress to strain. I'll call this 2A and this 2B, where these S and Q terms, right, consist of different relations between the material properties to plug in here. All right, so you can either solve for strains given the stresses, or solve for stresses given the strains using these S and Q terms. And so again, right, this is the result of superimposing those test results. So basically just combining them as though they were all conducted at the same time. And notice that the normal stresses, right, have no impact on the normal strains and vice versa. Or excuse me, on the shear strains, right? The normal stresses have no impact on the shear strains. Questions so far? Okay. All right, so now we're going to go back to the concept of strain energy that we talked about last time. And for that, all right, we're going to consider an element where we apply normal stress sigma 1 and then also a normal stress sigma 2. The strain energy density would then be equal to 1/2 sigma 1 times normal strain in the 1 plus 1/2 sigma 2 times strain in the 2 minus sigma 1 times Poisson ratio subscript 2(1) times sigma 2 over Young's modulus in the 2. And if we reverse the order of the stress application, applying sigma 2 first and then sigma 1, the strain energy density, and I'm actually going to go ahead and add subscripts to the strain energy density as well. So consistent with the order of stress application, the first one would be 1, 2, and then the second one would be 2, 1. So the 2, 1 order would be 1/2 sigma 2 times normal strain in 2 plus 1/2 sigma 1 times normal strain in 1 minus sigma 2 times Poisson ratio subscript 1, 2 times sigma 1 over Young's modulus for the one direction. So there's a difference. Order of application matters in this strain energy density calculation, right? So it doesn't affect the stresses, but for the strain energy density, there's a difference in that calculation. However, if the material is elastic, the matrix is symmetric. So that means we have reciprocity. In other words, we would have Poisson ratio over E2, Poisson ratio subscript 2(1) over E2 is equal to the Poisson ratio 1, 2 over E1. In other words, nu 2, 1, capital E1 is equal to nu 1, 2, capital E2, which means that the S12 term should be equal to the S21 term, and the Q12 should equal Q21.
What is the S and Q?
Those are the ratios or the relations between the material properties that relate stress to strain, so the constitutive relationships. Yeah. And they were defined on the previous page. Yeah, so those are defined on the previous page. All right, so now if we start making some substitutions, then we would end up with what we see here. So this shows the process. All right, so we want our normal strains in X and Y, all right? So that's the end goal in this example, right, this demonstration. So here, if we substitute in our first coordinate transformation, so this would be 1b and 2b, and then by making those coordinate transformations, we are relating our stresses in XY to the strains in 1, 2. And then if we substitute in our equation 1c, that would get us that 1c. That would get us a relationship between the normal stresses and shear stresses in XY to the normal and shear strains in XY. And so we're simplifying this 3-matrix product term as Q bar. And if you were working in terms of, in the other world, right, with the S's, then it would be the S bar. And those equations are all written out on the next page of the handout, just for your reference there. And so the summary of the whole process all right, because it's easy to kind of get lost in the weeds with this. All right, the first phase is to relate the material principal axes, 1, 2, to non-material principal axes, x, y. All right, so that's applying transformation. And we have separate equations for working in terms of stresses versus strains. So depending on which one you're given, that will tell you which set to use. Then the second phase relates the normal stresses, right, I guess technically normal and shear stresses, right, to the strains in the material 1, 2 directions. All right, so that brings in the S and Q terms. I can say S or Q because for a given approach, you wouldn't want to mix them. And that depends on the constitution of the material. And then the last step would be to relate the stresses to the strains in XY. So really, you could switch up the order of, the first and second phases, of course, but the last phase can't be done until the other two are complete. And so you would either, to get there, you would either apply 1B and 2B and then 1C, like we did here, or you would apply 1A and 2A, and then 1D, if you were working, solving for strains instead of stresses. I know. It is, but when you break it down and follow the steps, it's manageable. Yeah. Yeah. So what we see in these equations, as it's noted down here, right, and this alludes to what I pointed out earlier, we see a coupling behavior between normal stress and shear strain, which does not occur in isotropic materials. So that shows up in these, right, once we complete the process, right? So up here we don't see that coupling, right? But by the time we get through the coordinate transformation and applying the constitutive equations, we have these non-zero terms, right, relating the normal to the shear, the normal to the shear and vice versa. So that's something that's unique to orthotropic materials, right? What it means is that an applied normal stress will cause a shear strain and vice versa. So for example, if we had this piece of material, let's say that the material axes are oriented something like that, so not aligned with X and Y. If we wanted to calculate, right, the effects of, or if we wanted to express the normal stress in X, right, if that's the only stress that's applied, it would be Q bar 1,1 times normal strain in X plus Q bar 1,2 times normal strain in Y plus Q bar 1,6 times gamma XY. All right, so getting that from the previous page, right, that's just following this first row in the matrix equation. And then, of course, if you have other stresses applied, you add those other rows. And then here's the definition of those Q terms. As you can see, they're pretty lengthy. They're all tied to the angle theta as well as, right, they bring in the Q terms that don't have a bar in them. So those are all items that would be plugged in here to make this even longer than it looks. So don't worry, I'm not going to ask you to do something where you have to figure out, all these things. The problems that you'll encounter in this class will simplify significantly from what it looks like it could be. And let's see, so for example, I did posted homework 2 before class. Let me see if I can pull that up. There's homework 1. Oh, it's going to make me sign in. Okay. All right, let's take a look. So homework 2, you got a couple problems here that are more circle. So one is in terms of stress. So that should be, pretty much review from EGen 202 and then, or 205. And then you've got a more circle problem in terms of strain. So again, that's very similar to how you apply it for stress. Just remember that the difference is you have that extra 1/2 term in those transformation equations, right? So, so keep that in mind for the shear strain. And then 2 problems here tied to Hooke's law. So one is going to be more of a 3D application, and then this one is a plane stress condition. So this is what I was referring to earlier, where you're going to be asked to calculate the change in volume, and you can neglect the strain product terms. Oh yeah, it even says so in the problem statement, neglect the product terms in the strains. Good. All right, and then the last problem is tied to today's lecture, so orthotropic material. You're given the following 3 tests that are done on the same material, and all of the normal stress applications have the same magnitude in each test. The difference is the orientation of that stress application with respect to the material. So you're asked to find, given this information, some of the material properties and strains, or I guess just one material property, and then the 3 strains there. So you're given the other material properties here, all right? So again, I do not recommend trying to go through and set up one of those matrix solutions, because you don't need to do that for this problem, all right? It would be easier to just kind of lay out what you know and then look at the equations and see what can I solve for readily first, start there, and then start working your way through the rest, okay? That's my recommendation. Don't try to actually go through and set up the matrices. I mean, you could try that, but it might be more work than what you need to do, right? All right, questions? This might be an early exit